In this first problem, we have to discuss the convergence of a bunch of improper integrals. So we're going to begin with the first one, this, and well, this is easy to analyze. But before we apply any test or whatever, we have to realize why this is an improper integral. Well, of course, it's an improper integral because the upper limit is infinity. But notice that you have power here, and p has no constraint. I mean, p could be negative or even smaller than 1. So this integrand would be divergent in 0. So this could be improper for two reasons. It's improper of the first kind because there is an upper limit which is infinity, and it may be improper of the second kind in special cases where p is negative or smaller than 1 because of the 0 that you have down here. Okay, so the first thing we need to do is to split this integral in two. So we have this, and we separate the two cases by splitting it at, let's say, 1. Doesn't matter the point you choose. Okay, so 1 is a convenient point. Then you have the integral from 1 to infinity of the same integral here. All right. Okay, and now we have to analyze the two cases separately. So let's focus on this second integral here, right? We have already analyzed this case in an exercise in class. Turns out that this integral converges. Well, first of all, the integrand here is a positive function, right? It's always a positive function. Okay, so we can apply this for positive integrands. And this integrand converges for every value of p that you put here. And the reason is, if you compare this function when t goes to infinity, e minus t, tp minus 1, with the function t minus 2, well, it turns out that this is just the limit when t goes to infinity of the exponential times tp plus 1. And it doesn't matter what this power is, the behavior of this in the limit t infinity is controlled by this exponential. The exponential goes to 0 faster than this goes to infinity, so this limit is equal to 0, whatever the value of p. And on the other hand, we know that this integral here converges, right? This is the integral of the function that you have in the denominator here. So according to the limit comparison test in the second version, this integral converges always. So this one is not a problem. Now let's focus on this one here. Now for this one, the exponential is not a problem, right? The exponential is a well-behaving function anywhere between 0 and 1, right? It's a continuous function, it's an arbitrarily differentiable, whatever. Near 0, this function looks like this. It's 1 plus O1 when t goes to 0. So essentially, when t is very close to 0, this behaves just like a constant, right? So this integrand here, the whole integrand, tp minus 1, is equal to tp minus 1 plus otp minus 1 when t goes to 0. So what this means is that instead of studying this more complicated integrand, we just need to study this one in that limit, right? So what we're going to do is to see if this integral here converges, or if it does, for which values of p converges. All right, we know the behavior of this, right? We know that this integral converges if and only if, well, actually, what we have is this result. We have that this over t2 alpha from 0 to 1 converges if and only if alpha is smaller than 1. Okay, remember, if you have the integral from 1 to infinity of this same integrand, then the condition is alpha larger than 1. If you have from 0 to 1, the condition is alpha smaller than 1, right? So alpha in our case is 1 minus p, right? Because alpha is the power of t in the if it is in the denominator, right? So this has to be smaller than 1, which means that p has to be positive. So for any positive p that you can put here, this integral is convergent, right? So this integral converges. There's no problem at infinity, right? The only problem can happen at 0, and it converges as soon as p is positive. So even sometimes when the exponent here is negative, still the integral is converging. But the only condition is that p has to be a positive number. All right?